Hey guys, today I will present a solution to EGMO 2016 problem 1. Let x1 up to xn be non-negative real numbers such that n is odd. We write xn plus I is equal to xi for the sake of notation, and now we are asked to prove that the minimum of xi squared plus xi plus 1 squared for all indices I is less than or equal to the maximum of 2xi, xi plus 1 for all indices I. We know that at any particular index I, by AMGM, xi squared plus xi plus 1 squared is of course greater than or equal to 2xi, xi plus 1. If we can find indices I and j such that both xi and xi plus 1 are less than or equal to both xj and xj plus 1, then of course xi squared plus xi plus 1 squared is going to be less than or equal to 2 times xj, xj plus 1 anyways. Instead of taking a look at unrelated indices I and j, let's take a look at 3 consecutive values, xi minus 1, xi and xi plus 1. They are also made up of 2 pairs, namely xi minus 1 xi and xi plus 1. If xi lies between the other 2 values, then we are exactly in the case that I have previously described. So, for instance, if we have xi minus 1 less than or equal to xi less than or equal to xi plus 1, then we can conclude that xi minus 1 squared plus xi squared is less than or equal to 2 times xi squared, which is in turn less than or equal to 2 times xi plus 1. From that, we can bound this minimum from above by xi minus 1 squared plus xi squared, which we can again bound by 2xi, xi plus 1, which is a lower bound for that maximum, and thus we are done in this case. Analogously, we can finish if we find an I such that xi minus 1 is greater than or equal to xi, which is greater than or equal to xi plus 1. Therefore, we know how to deal with this problem if our sequence contains three increasing terms or 3 decreasing terms. And to finish our proof, let's assume that we have none of this. But in that case, our sequence must look something like this. Because n is odd, this kind of picture shouldn't be possible at every point, and we're going to show this in the second part of our proof. To do that, let us define for any index I the value di as xi minus 1 times xi minus xi plus 1. Thus, di is less than or equal to 0 if and only if we have this case, namely xi minus 1 less than or equal to xi less than or equal to xi plus 1, or the other one where xi minus 1 is greater than or equal to xi greater than or equal to xi plus 1. Because di is equal to negative xi minus 1 times xi plus 1 minus xi, and we see that in this representation both of these terms are equal with an index shift by 1, we may notice that if we multiply all of these values for I equal to 1 up to n of di, then we get each of those terms exactly twice and n minus 1 terms. So all of this is equal to minus 1 to the power of n times the product for I going from 1 to n of xi minus xi minus 1 all squared. We use the fact here that n is odd, which implies that negative 1 to the power of n is equal to minus 1, and so this product is less than or equal to 0. Therefore, not all di terms can be strictly positive, and in other words, we find an index I0 such that d I0 is less than or equal to 0. By this equivalence, this means that I0 is exactly of the form such that xi minus 1, xi and xi plus 1 look like this or that, and we have already discussed that from this we can deduce that the problem statement is true, and therefore we are done.